example, suppose we have two particles, each of which can be in one of two different single particle states or modes, A and B. So here are the two possible states, A and B. Suppose these particles are in some potential such that there are two single particle states or modes quite close in energy, and all other possible states are sufficiently far away in energy that we can approximately neglect those other states in our counting here. We might be considering, for example, two particles in a weakly coupled pair of similar quantum boxes, or a one-dimensional problem such as coupled potential wells. Here we get two energies that are quite close. Because we know for some other reason that the particles cannot have much energy, for example, the temperature may be low, we presume the particles can only be in one or other of these two lowest coupled single particle states or modes of these two wells or boxes. For each situation we consider, non-identical particles, identical bosons, and identical fermions, these single particle states or modes, A and B here, might be quite different, for example because of exchange energy effects. But that difference is not going to affect our argument here, which is just one of counting states. We can now write out the possible states in each case. For all of these cases, the number of possible single particle states or modes of a particle is m equals 2. So that's the number of possible single particle states or modes. And the number of particles we're going to deal with here is n equals 2. So these two particles here. For non-identical particles, such as a proton and a neutron, the possible distinct states of this pair of particles are particle 1 in state A, particle 2 in state A, so that's this one. They're both allowed to be in the same state. Particle 1 in state B, particle 2 in state B. Again, they're both allowed to be in the same state. Particle 1 in state A, particle 2 in state B. And the other way around, particle 1 in state B and particle 2 in state A. As we expected from our expression m to the power n, there are 2 to the power 2, which is 4, states of this pair of particles when they are non-identical. For bosons, if they are identical, such as, for example, two helium-4 atoms, and helium-4 atoms are bosons because they're made from 6 particles, each with spin 1/2, 2 protons, 2 neutrons, and 2 electrons, which therefore have an integer total spin, then the possible distinct states of this pair of identical bosons are particle 1 in state A, particle 2 in state A, particle 1 in state B, particle 2 in state B, and one particle in state A and one particle in state B. But there's only one such state like that, and that we've had to write out in the proper symmetrized form with respect to exchange. So there's only one way of having the two identical particles in different states. In this list of basis states here, that we wrote out for our identical boson case, we do not have to write the explicit symmetrized form like this, since it's describing the same state as this one. And similarly for the state with both particles in the B mode. It doesn't matter if we go to this form or not. It's not necessary. Here, the 1 over root 2, of course, normalizes the explicitly symmetric combination state. In this list of basis states, we therefore have 3 states, which agrees with our formula. Here's what we get if we calculate that out. Note that this is not the same as the case of non-identical particles, where we had 4 states. For identical fermions, there is only one possible state of the pair of particles, that is, with one particle in state A and one particle in state B. because the two particles have to be in different single particle states. And here there are only two single particle states to choose from for each particle. So that one normalized state is this anti-symmetrized combination here, which agrees with our formula, which gives 2 factorial over 2 factorial 0 factorial, which is 1, where we remember that 0 factorial is 1. The differences in the number of available states in the three cases of non-identical particles, identical bosons, and identical fermions leads to very different behavior once we consider the thermal occupation of states. For example, if we presume that we are at some relatively high temperature, such that the thermal energy, Boltzmann's constant times the temperature, which is a characteristic thermal energy, is much larger than the energy separation of the two single particle states or modes A and B, but still much less than the energy to the next states, then the thermal occupation probabilities of all of the different allowed combinations of single particle states or modes will all tend to be similar. For the case of the non-identical particles, which behave like classical particles as far as the counting of states is concerned, with our 4 states we concluded we could have there, so here they are, 1, 2, 3, and 4, we therefore expect a probability of 1/4 of occupation of any of these 4 two-particle states. Therefore, the probability that the two particles are in the same state is 1/2. 2 out of these 4 states correspond to having the particles both in the same single particle state or mode. For identical bosons, however, there are only 3 possible states. So the probability of occupation of any one state is approximately 1/3. 2 of the two-particle states have the particles in identical modes, and only 1 two-particle state has the particles in different single-particle states or modes. So the probability of finding the 2 identical bosons in the same single particle state or mode is now 2/3, larger than the 1/2 that we got for the non-identical particle case. For identical fermions, there is only 1 possible state, which is this one, which therefore has probability approximately 1 then in this situation, and it necessarily corresponds to the 2 particles being in different states. We can summarize our conclusions here. First, identical bosons are more likely to be in the same single particle states or modes than are non-identical or classical particles. Second, identical fermions are less likely to be in the same single particle states than are non-identical or classical particles. In fact, identical fermions can never be in the same single particle states. A common contrast between bosons and fermions is that we can have as many identical bosons in the same mode as we wish, but for identical fermions, of course, we can only have 1 in each single particle state. It's important to emphasize, though, that identical bosons also differ from the non-identical or classical particles. There are fewer states in which identical bosons are in different modes compared to the non-identical or classical case. So, though both for non-identical or classical particles and for bosons, we can have as many particles as we like in the same state, the statistics for bosons are not the same as those for non-identical or classical particles.